this is Brody, and this is going to be my ME304 final. So what we have to do is solve this combined loading problem. We have to find the principal stresses and maximum shearing stress at point H, which is here. So what I've done before is draw the diagram here with a cut section at point H and the loads. So the first thing we have to do is figure out the reaction forces at each axis, and then the moments. So this will be Rx, Ry, and Rz, and then each moment will be counterclockwise, assumed positive. There you go. And it'll be Mz, My, and Mx. So to find those, first thing we'll do, we'll make a table. With the position vector, the force vector, and the moment vector. I, J, K, I, J, K, I, J, K. And so the loads we have, I'm going to convert all the units to meters and newtons to make everything easier. So the first load is going to be 3,000 newtons on the x-axis. The second load is going to be 500 newtons on the y-axis and 2,500 newtons on the z-axis. So the position is going to be 0.15 meters in the x, 0 in the y, 0 in the z. Same thing for the next one. 1, 5, 0, and 0. And then for the last one, it's the same. It's 0.15 meters, 0, but then it's 0.16 down this way. And so for the force vector, it'll just be the loads that were applied to start with. So each load is negative on the given axis. So 3,000 newtons, 0 and 0. 0, negative 500 newtons, 0, and 0, 0, negative 2,500. And then to get the moments, you do position cross force, and that'll give you the moment. So the first one becomes all zeros. The second one is going to be 0x, 0y, and negative 75z, and then 0, 375 in the y, and 0 in the z again. So the Rx, Ry, Rz, Mx, My, Mz. And then these will literally just be the reaction that balances out these forces and moments. So the reaction here in the x is going to be 3,000 newtons. The reaction here in the y is going to be 500 newtons, and the reaction in the z is going to be 2,500 newtons. And then for the moments, there isn't one at mx. At my, it'll be this here, this 375, so it'll be negative 375 newton meters, and this will be 75 newton meters. And forgot to calculate the cross-sectional area. So it's a 40 millimeter by 20 millimeter rectangle, the whole cut section. So it'll be 0.04, excuse me, times 0.02, and that'll equal meters squared. And that will be our total area throughout. So the first force we want to look at is going to be the Rx. So when we're looking at the Rx, it's an axial force. Sorry, I can't spell. And the best way to do this is to look at it down the z plane, so that the x will be that way and the y will be this way, or on the xy axis. down the z, on the xy plane down the z-axis. And our point of interest, H, will be right about here. So then when we're looking at it that way, the force is going to be applied like that. And it'll be the 3,000 Newton force. So to find the stress here, it's pretty simple. Sigma x equals P over A, which equals force over area, which will just be the 3,000 over the area we just found, which will give us a sigma x of 3.75 megapascals. So then the next thing we're going to want to do is apply this to the stress blocks. And the stress blocks we draw in each plane. So it's the xy plane, the xz plane, and the zy plane. And so the force applied here, it's sigma x, so it's a stress in the x direction. So it's going to be on both of these stress blocks. Oh, sorry, I didn't label these. This is x, z, z, y. And each one will just be 3.75 megapascals and in compression. So the next part we're going to do, we're going to look at the Ry reaction force, and that'll cause a transverse shear. So the best way to look at this one, at first, you're going to want to look at it the same way on the xy plane. Oops, sorry. But the force you'll notice will be 500 newtons downwards. So you can't get a great, and H will actually be here. So you're looking at it, excuse me. I think H will be here. Like, once again, same plane. So you'll notice that the 500 is going downward and shearing it that way. So then the best is to rotate this kind of like the face towards you. So it'll look like this. And then it will be in the middle. And your neutral axis will run right through here. This will be point H, and this will be the area that we're looking at. And so the formula for transverse shear is going to be transverse shear in the XZ is going to equal VQ over IT. And V is the load, Q is Y bar prime times A prime. A prime is the outer area, and Y bar prime is going to be the distance from the neutral axis to the center point of the shape you're looking at. And in this case, A, there is no outer area since our point of interest is on the outer edge of the shape. So since A equals 0, that'll mean Q equals 0, and the entire transverse shear here in the XZ will equal 0. So since it's 0, you don't have to apply it to any stress blocks or anything. So next, we will look at RZ, our last reaction force. And once again, it'll be another transverse shear. So this one, we're going to look at it from a different plane at first again. And this one will be the XZ plane, I believe. So your point of interest will be right here in the middle. And the force will be 2,500 newtons downward again. So in the Z direction. And you got to flip it again. So this one, it's actually going to look like this, like when you rotate it towards you. So the shape will be like this. this will be here. Your neutral axis will run right through here again, and this will be the area you're looking at. So that'll be your outer area. This is 0.02 meters, and this is 0.04 meters. So, same formula. Shear in the XY this time will be VQ over IT. T is just thickness, and then moment. I is moment of inertia. So we can start plugging in what we know. So it's a 2,500 Newton load. Q we have to solve for. I we have to solve for, and then T we know is just 0.02 meters. So to solve for Q, like I said before, it is going to be Q equals Y bar prime A prime. And in this case, A prime is going to be this section here that's shaded. So this is 0.02, this is 0.02. 0.02 squared, or 0.02 times 0.02, is going to be 0.0004 meters squared. And then Y bar prime is going to equal 0.01, because our point's here, and then this is the midpoint, that's 0.02, 0.01. So Q is 0.01 times 0.0004, which will equal, sorry, I'm running out of room here, 4 times 10 to the 6, negative 6, excuse me. So, 6. I'm going to go to the next page here to solve for the I, but I'll just carry that over. So we were here. Oh shit. So now we have to solve for I, and in this case, since the shape was like this, we have to solve for the moment of inertia in the X direction, so that this will equal 1/12 base times height cubed. So then 1/12 0.02 times 0.04 cubed, I will equal 1.07 times 10 to the negative 7 in this case, and that'll be in meters fourth. So then we have everything. So XY equals 2,500 times, what was that? 4 times 10 to the negative 6 over 1.07 times 10 to the negative 7 times 0.02. And in this case, the shear will be 4.68 megapascals. So then apply that to the stress blocks. And since it's in the XY plane, it's a positive in the XY plane. So your shear will just be here. Ooh, and like I said, it'll be 4.68 megapascals. And then we will be moving on to the moments. So the first moment we don't have in MX because as stated earlier, it just became 0. So the MX will just go away, right? But the MY was the first moment we had, and it'll cause a bending moment. So the bending moment, we're going to look at it down the y-axis, so on the xz plane. And your point of interest will be here again. Neutral axis runs all the way through. So the moment was 375 Newton per meter, and it will be clockwise because it was negative. So 375 Newton per meter. And then this formula to find the stress in sigma y is going to be my over I, where m is the load, y is the distance from the point of interest to the neutral axis. But in this case, since the neutral axis runs through the point of interest, y will become 0. And once again, the whole thing, the sigma y will just equal 0. So we don't have to apply any stress blocks or anything to this either. And then the last reaction we have to solve for or work with is the mz, moment in the z, and it'll create another bending moment. So here, the best way to look at it is going to be on the xy plane, where your point of interest h will be here. And the moment will be positive this time, so that it is counterclockwise and is 75 Newton per meter. So same formula, sigma z this time equals my over I. We'll fill in what we know. .02, I think. Hold on. 0.01, my bad. The I we have to solve for again. So in this case, it's the same formula. But we're actually going to flip it since it's just oriented differently. Because like if you were to flip it this way, the rectangle would be shaped longwise again. So 1/12 0.04 times 0.02 to the third, and that will equal 2.67 times 10 to the negative 8th meters to the fourth. So that'll plop right in here. And the sigma z will equal 28.1 megapascals. So we apply that to the stress blocks now. Same stress blocks every time. X, Y. Drew these ones a little close by accident. It'll be fine now. And it's in the z direction. So, excuse me, it's in the x direction. It'll be this way again. So then that's the 28.1 megapascals. And it's on both of those planes. So then one of the last steps is we're going to combine all the stress blocks that we worked on so far together. So when we combine them, you basically take all the forces that you got throughout on each set and you add them all together and put them on one final set of stress blocks. So the only shearing stress we got was in the XY plane, and it was the positive 4.68 megapascals. And then we got two compressions and tensions. So when you add these up, I forgot to mention actually that, so this is actually a moment that will cause a force like this on the piece. So the top half will be in compression, the bottom half will be in tension. And so you subtract the, what was it? You subtract from the 28.1 megapascals, the other value we got. And so what you get here is a tension on both in the X direction of 24.4 megapascals. So those are our final analysis of the stress blocks, and now we have to find the principal stresses and maximum shearing stress. So to do that, the formula for principal stresses is going to be sigma x plus sigma y over 2 plus or minus the whole square root of sigma x minus sigma y over 2 squared plus txy shearing squared. So that's the formula. In this formula, the sigma x is going to be 24.4. The sigma y is equal to 0 since we had no stresses in the y direction. And shearing is going to equal the 4.68. So then it's just plug and chug. Sorry, I forgot the plug. When you plug this into the calculator, it will give you values of 12.2 plus or minus 13.667. And then sigma 1, which will be the max, will be 25.267 megapascals. And sigma 2 will equal a negative 0.867 megapascals. Yeah. So those are our principal stresses. And then our shear max is going to equal just the radical from the previous formula. So it's just sigma x minus sigma y over 2 squared plus xy squared. So then we already found that equals 13.667. So tau max equals 13.667 megapascals. Thank you.